turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to this week's Naked Scientists, the programme where we bring you the latest breakthroughs and talk to some of the biggest movers and shakers in the fields of science, technology and medicine. I'm Chris Smith, and this week, the titan of science who discovered the accelerating expansion of the universe and ultimately gave us dark energy. I'm talking to Brian Schmidt.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
A century ago, the stargazer Edwin Hubble shook the world of astronomy when he presented findings showing that the universe wasn't standing still. It was growing, blowing up like a balloon. But he could only look so far in space because his measurements relied on a class of stars called Cepheid variables, which throb in brightness with a regular rhythm that depends upon how large they are. So the rate of their pulsations told him how big they were, and that in turn enabled him to work out, based on their brightness, how far away they were. And that enabled him to show that the distances to farther off objects were growing with time. In other words, the universe appeared to be growing. What would happen, though, if scientists turned to far more powerful light sources that were always of the same brightness, but which could be seen over far vaster distances? Would they too hold true to Hubble's observation of a gently expanding universe? Well, this was the question that Brian Schmidt and his colleagues asked, and they used the dramatic supernova explosions, cosmic firecrackers as he puts it, that mark the end of a star's life. These enormous blasts are transiently the brightest lights in the universe, and they can be seen like beacons from literally billions of light years away. And what they reveal is that the universe isn't just growing, its rate of growth is speeding up, powered by an entity that we don't understand, we can't measure, and which appears to come out of nowhere, but which must account for the vast majority of what is actually out there. And that entity is dark energy. These observations were a seismic revelation in cosmology, and they earned their discoverers the 2011 Nobel Prize. Brian takes up the tale of how he came to be working on this problem in the first place and where it ultimately led him.
We were a little confused at the time. We had been struggling to measure how fast the universe was expanding, something we knew about since the time of Hubble. The problem we had is we had two groups trying to measure it, and they were getting very different answers. And one of the answers, favored by a lot of sensible people, seemed to be in discord with the age of the universe. Because if you measure how fast the universe is expanding, you can then run the universe in reverse and find out when everything was on top of everything else. That's the time of the Big Bang. So I came in at a time with a lot of uncertainty and was very keen, therefore, to measure the expansion rate of the universe with a new method, type 2 supernovae, that was a little different than what everyone else was using.
What had Hubble done then? Because you came at this armed with the knowledge and his observations from many, many decades before. What did he show?
So Hubble went out in 1929 and measured how bright objects were, and he compared galaxy stars and galaxies, and he wanted to see what the relative distances of galaxies were by comparing how bright their stars were. So the further an object is, the fainter its stars are going to appear. And he also used data from someone named Vesto Melvin Slipher. Most people have never heard of this guy, but he's half the deal. And Slipher had measured how much the light from these galaxies had been stretched by their motions, or at least what they thought were the motions. And what he mysteriously found in 1917 was that every object was stretched redward, indicating the Doppler shift was saying they were moving away from us. And that was a big surprise. But Hubble realized that in an expanding universe, that's what you get. Everything's moving away from you, and the further something is, the faster it's moving, which is what he saw when he compared his brightnesses of stars and the distances that he'd figured out from them with Slipher's redshifts or motions of galaxies.
So we had an idea that the universe was getting bigger. Things were moving apart. Did we have any idea as to how fast they were doing that at the time?
So at the time, there were two numbers and an astronomer's units, which are kilometers per second per megaparsec, which I don't expect your listeners to understand. The numbers came as about 50 and maybe 90, which corresponds, if you just run the universe in reverse with that number, to an age of the universe between 15 billion years or 10 billion years. And we were pretty sure at the time that the oldest stars were at least 13 billion years old.
Did they think then, if they saw things, distant objects, moving away from them, that space was infinite and these things were moving away from us through space? Or did they actually have a concept that the space between us and those distant objects was getting bigger, making them appear to be moving away? When did that kind of change or view shift?
So we knew, since people thought through Einstein's theory of general relativity, which says that gravity curves space, that a heavy universe would be curved onto itself in the shape of a sphere, and a light universe would be curved away from itself in the shape of a saddle. And then the just right universe, the one that had just the right amount of stuff in it, would actually be flat and kind of look like what we think of life looking like here on Earth. So it was the big question, wouldn't it be great to be able to go and measure the shape of the universe?
And why were there those two different numbers? If people were just measuring objects, moving away from us, seeing how far the universe appeared to be stretched in the interim, why did that give two values that were quite disparate?
Turns out it's really, really hard to measure distances in space. You can't just put a ruler down. And so we had photographic plates. Photographs are good for looking at things, but they're terrible for measuring things accurately. We had, because of that, not developed precision methods for measuring distances. We had Cepheid variable stars, which were by far and away the best thing, going way back to Hubble. But they only are bright enough to be seen in the very nearest parts of the universe, where the universe really isn't expanding because there's too much gravity around from us and everything else. So it really took the development of technology to allow us to start measuring the numbers accurately. And so that happened right at the time I did my PhD thesis. I was born at the right time. I had access to the first digital data on stars, and I used the brightest stars there are, exploding stars, supernovae, to measure the distances. So type 1a supernovae are these giant thermonuclear firecrackers, and they are very well behaved. It turns out no matter how you blow them up, they kind of do the same thing. They're just a firecracker. It's like a piece of TNT, and it doesn't matter if you light it with a fuse or you kick it with a hammer. When it blows up, it's still a big piece of TNT. So they are remarkably uniform compared to most things in the sky. And it turns out that just by measuring how long they take to explode, that tells you to within 5% in measuring distance how bright they are.
Were you looking for the light, or were you looking for other things that come out from supernovae, things like the X-rays that they blast out? What was your signal that you were looking for when you were doing this work to spot them and then record the distance?
So this has changed quite dramatically. In 1990, we had amateurs. There was a reverend in Australia who very famously could memorize the nighttime sky and just point his telescope and say, there's a new star there. And he would phone them in and we'd look at him, and sure enough, he was right. Then we got digital cameras, new technology. We went away from photographs, which were a real pain to go and find exploding stars because you have to go develop it and weeks pass. So these digital cameras allowed us to use computers and start scanning all the nearby galaxies. So we were out using optical light, looking for new stars that appeared around nearby and progressively more distant galaxies.
And when you say the appearance of new stars, these are stars that appear because they are blowing themselves up and becoming very bright.
That's correct. So the star was there, it just was a billion times fainter, and so when you look at it, you couldn't see anything. It was just black. And then suddenly, it's as bright as a billion stars, and it really does shine at that point.
This gives you a wealth of data, so you can go well beyond Hubble. When did it become apparent what the real number was then? Where between those two extremes that were born out of the inaccuracies of the recording measures that they were using decades ago, what the real number for the expansion of the universe was?
So in 1993, for my thesis, I measured a number that was almost directly in between. The number was 73. That gave an age of the universe of about 14 billion years. It made everyone unhappy. The people got the high number thought I was wrong. The people got the low number thought I was wrong. And I would say I was not absolutely convinced I had nailed it, but at least it was a good try. The thing that really broke, I think, the deadlock was the Hubble Space Telescope technology that allowed us to go through and go out an order of magnitude further, that allowed us to calibrate a whole bunch of supernovae using them, and then it became very clear that the number, it turns out, was around 70. So I got, I think, a gold star, and that number 70 has been refined over time, now with James Webb Space Telescope, the Hubble for many, many years. Adam Rees, my colleague, has really spent 20 years doing this, and he gets, 73 and a half, plus or minus a very small number, which in itself is very interesting.
The implications of that number are that not only is the universe getting bigger, but as it gets bigger faster. It's blowing up. How did that become apparent?
In 1993, I had done that work to measure how fast the universe is expanding now. That technology that allowed us to start measuring the Hubble constant accurately, these digital cameras, suddenly allowed us to start looking at supernovae, not just millions of years in the past, but billions upon billions of years in the past. So suddenly what became possible using type 1a supernovae was to measure how fast the universe was expanding in the nearby, like the last 10, 50 million years, and then compare it to objects that were 10 billion light years in some cases. And so we were able to then see what the universe was doing, and was it slowing down a little bit, or slowing down a lot, or not slowing down at all? That's what we thought, were the possibilities in 1990.
What did you think? Did you think that it was just a continuous rate of growth then? Or were you prepared to accept that actually we could have been wrong? It's gone through various phases over its lifetime. What was your thinking?
So the theory at the time was pretty straightforward. The heavier the universe, the more it slows down over time. And so we were going to measure how much the universe slowed down. And the more the universe slowed down over the time that we looked at it, the heavier the universe was. And so we're essentially just going to weigh the universe. And by weighing the universe, we could actually figure out, was the universe going to slow down so much that in the future it would stop, go in reverse, and we would have, as I always like to refer via Douglas Adams, the Gnab-Gib, the Big Bang in reverse. Or was it going to expand forever and not slow down enough, so it just kept on going for eternity?
Did it kind of concern you then that when you began to get the numbers in, it didn't seem to fit the Big Bang in reverse type model? Did you think we're getting something wrong? Or did you think, actually, this is really exciting, it's not going to go into reverse?
Our first object that we got really good data on it, and it was showing that the universe was expanding slower in the past and sped up. And that bothered me because that was not a reasonable answer. But it was one object, and we're like, okay, we're going to get more objects, see what happens. And at the end of 1997, Adam Rees emailed me a figure of the preliminary results on where we were up to that time, and it very clearly showed that this was not an anomaly, but all the objects seemed to be showing that the universe was expanding slower in the past and had sped up. So that was not me yelling eureka immediately, quite the opposite. It was, all right, we have screwed up something. We need to go through systematically and do everything from scratch with me doing the stuff you did and you doing the stuff I did and making sure everything had a separate, completely independent channel on it. And so that took a few months, as you might imagine. But after that couple months, the numbers didn't move around at all. And so we had to live with it by the beginning of 1998. We weren't going to make this go away.
That left you with a problem, of course, because we understood gravity. Gravity pulls things together. But if the universe is growing, and the faster it goes, the faster it grows, which is what you effectively saw, you had to come up with a way to explain that. So was there some pushback, or were people saying, well, how, Brian, do you explain this, possibly, that out of empty space comes some way for the universe to fuel its own growth faster?
So like most good things in cosmology, Einstein had actually already come up with the answer. So he had realized in 1917 that his equations of gravity allowed something he called the cosmological constant to be there. He thought up that as a possibility because in 1917, when he was looking at his equations for the first time, he realized they indicated that the universe would be in motion, and he thought the universe should be static. And this was a way he was going to balance out the effects of gravity, because this term, it turns out, naturally balances gravity. It actually makes gravity and the things in the universe that are full of this cosmological constant repel as opposed to attract. Now, in 1998, when we made this discovery that the universe seemed to be accelerating, we knew immediately we could use a cosmological constant. And it turns out the amount of cosmological constant we needed was an interesting amount, because it brought the total amount of stuff in the universe to that magical number where the universe is neither curved away from itself or onto itself, where it's flat. And that's a magical number because the theorists working through something called inflation were convinced that that was the only sensible shape for the universe, was for the universe to be flat. And this fixed that issue. So rather than being highly skeptical, many of the community were actually kind of ebullient in saying, this must be the answer. It fixes everything. It makes the age of the universe right again. It causes the universe to be flat, and all these things. It had many, many good things at solving the issues of cosmology at the time.
You still, though, had to explain the how, the mechanism, what is causing that expansion. And that, presumably, is where dark energy comes in.
Yeah, so dark energy is the word we use to describe the cosmological constant or anything else like the cosmological constant that might be there. Now, the cosmological constant you can think of as being energy that is in every part of space, always, never changes, it's always there, and that characteristic is what makes gravity push rather than pull on it. So dark energy, the cosmological constant, was our solution. As I said, we call it dark energy now, just in case it's changing a little bit over time and allowed. But whatever it is, it looks an awful lot like what Einstein developed all those years ago. But we have no idea why it's there. It just seems to be there at this point.
Researchers have been looking at the density of the dark energy. There's a project which is studying enormous swathes of space and distant space to work out the density of the dark energy in those different places. If it was just fixed, it would be relatively easy to explain. They're saying that they look in different places and at different stages of the universe, and dark energy isn't just pushing with the same amount. Its density is changing over time. So is that a spanner in the works then?
So this is very recent work that's gone on up to this point, from 1998 until 2023. Every measurement had sort of shown that it hadn't changed its density at all. It seemed to be absolutely constant back in time. Over the last 9 months, there's been a few experiments that are getting better and better data that seem to see hints that it is changing back in time. That would be exciting at some level because it would be something different than Einstein's cosmological constant. It's not what he predicts. It's got to be something else. And one of the problems with Einstein's cosmological constant is that it's kind of generically emerges from a whole bunch of different types of theories, and it's almost impossible to test, therefore. But if we see something that's a little different than it, that is much more peculiar probably to the correct theory, and so I think will make it easier to understand what's going on. But I need to caution everyone. This is very preliminary findings at this point. These are very hard measurements, and there are great teams that have done it. But I'd like to see over the next 5 years, we're going to get a lot more data, and I want to see if this answer of it changing over time persists.
Because the implications of it changing over time are that its effect is being tweaked somehow. Something is changing the potency of dark energy, and therefore the outcome of its presence. So that will change the behaviour of the universe. So it isn't just going to be a case of the universe grows and grows forever. It could alter its evolution as it evolves.
Indeed. If we want to understand what the future of the universe, so up to this point we've assumed dark energy has no reason to go away, and so we would expect it to push the universe apart faster and faster over time. But it also helps us hopefully understand why dark energy is there to begin with. We have this mystery of how quantum mechanics and gravity work together. Maybe this will be a clue of how to explain dark energy emerging from those two forces, or maybe it has nothing to do with it. There's one other issue that's out there, which is my colleague Adam Rees has, as I said, made those measurements very accurately over the last 20 years of the Hubble constant with James Webb Space Telescope now and Hubble before. And the number he gets doesn't quite agree with what we expect from the other really precise measurement we've made of the universe, the cosmic microwave background. They're about 8% off. So maybe we just don't understand what's going on well at all. That's a distinct possibility. And that would be really exciting for an astronomer. But as I said, I feel like we need to get some better data now because we're all a little confused again.
We first met in 2007 here in Cambridge when you were going to get the Gruber Prize, which many say is often an antecedent to getting the Nobel Prize. And you get the Nobel Prize, and then you become the Vice-Chancellor of the Australian National University. So why did you decide to go from really very cutting-edge research into running a university? Because they're very different. I mean, similar, but they're very different jobs.
They're very different jobs, not much in common between the two things. I did it because I wanted to make change in how universities intersect with society. I was concerned that universities were losing their way. I felt that in losing their way, I would probably be faced in the not too distant future of not actually being able to do the research that I had, done for the previous 25 years. And that seemed to me to be a bad outcome, not just for me, but for society. So it was nothing that was ever on my agenda until after I won the Nobel Prize. And it was after about 3 years of winning the Nobel Prize and getting frustrated about trying to convince people that universities and research and teaching well and all the things that we do here have really good flow-on benefits for society. So it really goes back to the core of how humanity has progressed.
You did 8 years in that role. You've now stepped down from that. Have you gone back to research? And did you manage to keep a hand in with your research that won you the Nobel Prize?
So I'm over in England right now on sabbatical, just finishing up a 4-month time. It turns out I have a vineyard and a winery, which people will know about. And this is the 4-month winter break where I don't need to be in Australia. So I've been reconnecting with my field. And so as Vice Chancellor, I managed to stay connected to my field until COVID. And then when COVID happened, I could not sensibly take on students and postdocs, so I didn't. But now I'm back, and I'm focusing on the supernovae again that I started on. The data capabilities that have emerged in the last 8 years are amazing, truly astronomical. And so I've been working at Oxford with a group looking at this data set that finds 25 supernovae a week And I mean, that used to be the entire year's worth. So I'm a kid in the candy shop learning how everything's working. But I have to admit, trying to get my brain to get out of administration and, programming in Python and things again is been slow and hard.
Yeah, we're on to 3 point something now. It must have been in the 2 point somethings when you were doing.
We were already in the threes. The problem is that the 3 threes or whatever I used back 8 years ago, nothing seems to work anymore. So it's a bit of a nightmare.
I've had that problem. They break lots of things, don't they? This vineyard then, where's that?
So I live on a farm just outside of Canberra. So we have 35 hectares, 88 acres in the old way of saying things. And yeah, I have a little vineyard and make a Pinot Noir, making a little bit of Shiraz Viognier to hedge against climate change. But we had really cold weather the last 4 years in Australia after just blistering hot years beforehand. And so I'm not about to get rid of all my Pinot Noir yet.
Were you a fresh starter? Did you come to this cold, or did you already know what you were doing when you took on the vineyard?
I came at it absolutely cold, and, I have learned, but we're doing pretty well. I'm making far better Pinot Noir than I ever thought I would, and I even have a good review from Jancis Robinson.
Really?
Indeed.
How much do you make? I don't mean cash. I mean as in how much do you actually churn out?
So it's a small vineyard. For those who are into wine, it's about half the size of Domaine Romani Conti. I don't get $20,000 a bottle for my wine, as you might imagine.
Yeah.
Not yet. But it depends. The weather is finicky in Canberra. It's actually quite cool there for anyone who's ever been there. So we typically try to make, I should be making between 2,000 and 4,000 bottles a year.
Darrenburg in South Australia had a very nice bottle of wine that was the Noble Prankster. Yes. And I saw that and thought, you could make the Nobel Prankster.
So Nobel Foundation has discussed that there is copyright on the name Nobel that would be enforced, but that they would be happy to discuss with me. And I am thinking about doing this actually before I die because it would be fun, of making a Nobel wine, which they would serve at the Nobel ceremony. So we'll have a discussion about that because I need kind of 5 years to get it in good shape. And they drink a lot of wine at the ceremony. So you got to make a lot of wine.
I'll raise a glass to that, Brian. Thank you very much to Nobel Prize winner and discoverer of the accelerating growth of our universe, Brian Schmidt. Next week is the final Titan of this season when we'll be joining the body clock biologist Russell Foster, who discovered how our eyes sense the start of the day and tune our sleep-wake cycle. He reckons he's got a drug to cure jet lag. And it's not just a gin and tonic and 2 Valium on the plane. Tune in next Tuesday to hear how it works. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith, and from all of us here on The Naked Scientist, thanks for listening, and until next time, goodbye.